Now we move on to the latest development of speech synthesis from a hidden Markov model to deep neural network. So, and the deep neural network approach is based on the deep learning revolution. In order to have a good understanding of the deep learning revolution, we can have a brief overview of the development of a neural network approach. The earliest neural network came out in 1960s as the form of multi-layer perception. And then in 1980s, the back propagation algorithm was invented. And at that time, people can only train very shallow networks. By shallow, I mean only a network with 3 layers. If you go into more layers of network, then very often you cannot make the training converge. So that's the difficulty at that period. And then came the deep learning revolution. The deep learning revolution exactly focus on the training of the deep neural network. Because in 1980s, people cannot train a deep neural network. But in 2016, in 26, engineers figured out a way to train a deep neural network. The approach at that time was to use pre-training. And after this new development, in 2010, people applied the deep learning in the field of automatic speech recognition and made big progress. And after that, deep learning method was applied in the field of text-to-speech in 2013, 3 years later. So that's the major milestones in the development of the neural network approach. And we can see the current development in TTS was based on the deep learning revolution, which started in 2006. We can do a quick comparison between the deep neural network and the hidden Markov model. And the major difference is that the deeper neural network has much more modeling power than a hidden Markov model. Based on that, with the deeper neural network, we can model a much longer sequence, well beyond the phone scope. As we said before, due to the weak modeling power of a hidden Markov model, we can only model a phone level sequence. And even for that, we have to do further divide and conquer. We use the decision tree first and then do the real hidden Markov modeling for those clusters. But with the deeper neural network, we can model a much longer sequence. We can model a sequence of phones, not just the phone. And also we can do a very large mapping. Again, in the traditional approach of TTS systems, we use the divide and conquer. The major reason was that the general mapping problem was very complex, and since hidden Markov model is very weak, we have to do divide and conquer. But with the more modeling power of a deeper neural network, we can model a very complex mapping that will greatly simplify the divide and conquer strategy. So we don't need to divide the mapping into more subtle sub-mappings. We can do more than one sub-mapping together. So all these are based on the much more higher modeling power of the deep neural network. So in applying deep neural network technology into TTS, there are also different phases of development. At the very beginning, people are based on the traditional HTS system. They are just trying to replace a tiny part of that traditional system. So the first approach is to replace HMM modeling with the deeper neural network model directly. As we can see here, people are still using decision tree first. But in the clusters, instead of using the hidden Markov model to model the phones in the clusters, they're using DNN instead. So that's the first approach in the application of deep learning method in TTS. Another approach moves further in the direction of deep learning. In this case, we can see it goes directly from context features to acoustic features. In this way, it bypassed the decision tree. So in this case, we don't see decision tree. And also it bypassed the probability density function. So it goes directly from context features to acoustic features by using a deep neural network. So these are the two earliest applications of deep learning in TTS. Big progress was made with the invention of WaveNet. In all the traditional approaches, we have to model the acoustic features. So because the samples in a speech is very many, because normally we use like a 16K sampling rate, which means in a second, even in a second, we have 16,000 samples to generate. So due to this large number of samples, we cannot generate samples directly. We have to generate acoustic features as an intermediate step. And the acoustic features are much, the number is much less than the number of samples, because acoustic features is a frame level features. So a frame could contain many samples. So the acoustic features is much less than the number of samples. But in a WaveNet, it directly generate samples. So that's the major progress. It happens in 2016. So these are the key ideas in a WaveNet. Again, because the deep neural network is much powerful than the hidden Markov model, now we can use it to model waveform samples directly. In this case, we bypass all the signal processing method. We don't need to do all those kind of signal processing to generate acoustic features. We can handle waveform samples directly. That's the very important, the most important features of WaveNet. And in WaveNet, convolution was adopted was transferred from the field of image processing. Because originally the convolution was used in image processing, and image is a 2D data. But speech is different, because speech is just a one-dimensional sequence. But in this case, engineers transferred this convolution idea from the field of image processing into the field of speech processing. And also another feature is of WaveNet is autoregressiveness, which means it generates samples based on previous samples. So it generates samples one by one, but the current sample is based on the previous samples. And in order to generate a meaningful speech, linguistic context has to be used to condition the network. The basic WaveNet just models the dependence between the symbols. But in order to make a meaningful speech, linguistic context are necessary. Specifically, it's used to condition the WaveNet. A further development out of the WaveNet is the WaveNet vocoder. So in the original WaveNet, people used linguistic features to generate symbols directly. But then people think, why can't we use the acoustic features to condition the network? Then we will have a new type of vocoder. So this diagram shows the difference between the traditional vocoder and a neural vocoder. In a traditional vocoder, it's based on signal processing. All the mapping is done by signal processing, and this is a mapping from acoustic features to waveform samples. So that's the traditional approach by using signal processing. But in this neural approach, at the middle is the WaveNet. But in this case, it's different from the original WaveNet. In the original WaveNet, linguistic features were used to condition the WaveNet. But in this case, acoustic features were used to condition the WaveNet. Then again, we have a mapping from acoustic features to waveform samples. So we have a WaveNet vocoder. So this WaveNet vocoder was invented right after WaveNet in 2017. So the previous one is the development in vocoder. Then people inspired by the WaveNet, they are trying to make progress also in acoustic modeling. So that the Taikotron 1 and Taikotron 2 are the first result of this effort. Taikotron 2 is very popular and even still popular in these days. It's invented in 2018. The structure of a Taikotron 2 consists of mainly two parts. One is the encoder, which is colored light blue in this diagram. And the other one is the decoder, which is colored orange in this diagram. So at the bottom of the diagram, the input text comes into the system was encoded by the encoder. And then between the encoder and the decoder, there is the local sensitive attention. And after that, the intermediate vectors are processed by the decoder to generate the final Mel spectrogram. So that's the basic structure of a Taikotron 2. It's a neural approach for acoustic modeling. Let's see some core ideas in this new acoustic model. Again, this model is based on a deeper neural network. We can see in this new way of acoustic modeling, it maps acoustic features directly into, it maps text directly into acoustic features. So in this way, it bypasses the linguistic context features. So we can see in the traditional divide and conquer approach, actually the first two mapping are combined together. We go directly from text, bypassing the linguistic features and go directly to acoustic features. Another important characteristic of Taikotron 2 is that Mel spectrogram alone is enough to represent acoustic properties. So in a traditional approach, besides the spectrogram, we also use F0 and the duration these other acoustic features. But in this case, we only use a Mel spectrogram. So that's another important feature of Tachytron-2. Also, in a diagram, we see that between the encoder and decoder, there is the attention component. So local sensitive attention is another essential part of this new acoustic feature modeling. I mean, the major function of this local sensitive attention is to model the context of a particular unit. So that's the also another core part of this new architecture. Again, like WaveNet, the acoustic features in this case is generated one by one autoregressively, which means the current frame, the acoustic features of the current frame is based on the acoustic features of previous frames. So we have this dependency here. So these are the basic ideas in a Tachytron-2 architecture, which is a very popular acoustic modeling. And but Tachytron-2 has some disadvantages. One thing is that it's the training of Tachytron-2 is very slow because it has that local has the convolution network and recurrent neural network. So these are the things which causes the slow speed of training. And in a new acoustic model, acoustic features model, it tries to remove those disadvantages. This new acoustic model is called a transformer TTS. Transformer was originally invented in the field of machine translation, and then was again transferred to the field of speech processing. The key idea of a transformer is to only use a multi-head attention to modeling a longer distance. In this case, the convolution neural network and recurrent neural network were removed from the system. So in a transformer, there's no, in a diagram, you can see there is no convolution neural network or recurrent neural network. Those are very slow to train. And in removing these components from the network, the training speed is much faster than the previous Tachytron-2 architecture. Because in a training, it can do parallel training. But again, in inference, in generating the final acoustic features, still it's done autoregressively. Which means the current samples, the current frames are generated based on the previous frames. So we still have this autoregressive feature here, and this is a disadvantage that will be overcome by later development. So the previous two architecture are developments in an area of acoustic modeling. And after the WaveNet vocoder, I mean, more development in vocoder also happened. And the original WaveNet vocoder, I mean, the major shortcoming is the speed. It's very slow because it's autoregressive. The generating of samples is autoregressive, which means it has to, the samples has to be generated one by one. So a new development is to overcome this shortcoming. People trying to make the generation of samples can be done in parallel. A solution for this is the flow-based WaveNet vocoder. And there are two major implementation of this flow-based WaveNet vocoder. One is the flow WaveNet, and the other one is WaveGlow. They are just a different implementation, but they are essentially the same. The basic idea are the same. They both use flow to do the mapping. So here are the basic ideas of the flow-based WaveNet vocoder. I mean, the general idea is to make the generation parallel, but it's based on the flow. I mean, why a flow can achieve that, achieve the parallelism? A flow is a reversible probability distribution transformation. So this is based on some mathematics. So they're using flow because flow has this very good feature. It's reversible. That's the major feature of this kind of flow. It's a reversible probability distribution transformation. And during the training of the acoustic model, the flow goes from a sample distribution. So the samples are treated as a distribution. So during the training phase, we go from the sample distribution to a normal distribution. So that's the mapping used during the training phase. In this phase, the architecture also used the acoustic features as the condition. And in the synthesis phase, it goes backwards. Basically, it goes from a normal distribution to the sample distribution. Since the source is a normal distribution, so there's no dependency between the samples. Because a normal distribution is a common target, a common source. We can go there directly and generate the samples. So this is the key idea of realizing the parallelism, because by using this flow, we can go from a normal distribution directly. So there's no dependency among the samples. For each of the sample, we can generate them in parallel. We can just go from a normal distribution and by using the flow to compute the sample distribution. So that's why a flow-based WaveNet vocoder is much faster than the original WaveNet vocoder, because it has this parallelism. And the key foundation is this reversibility of this kind of flow. So this is a further development of vocoder. So now we can do a summary of the 4 stages we talked about of the development of speech synthesis. Originally, we have the physical simulation of a human vocal tract. And the typical example is the speaking machine. And this earlier phase was improved with the development of signal processing. After the signal processing, engineers have a new way of simulating the human vocal tract. Basically, now they can use signal processing to simulate vocal tract. So compared with the original physical simulation, this is a functional simulation. And the typical examples we talked about are VODA and OVE. Then came the paradigm shift. It's a shift from speaking to speech. So engineers moved away from simulating human speech production process and modeling the speech itself directly. So that's the paradigm shift. After that, we have the data modeling approach. And the model used was the hidden Markov model. But the modeling power of a hidden Markov model is very weak. And then came the deep learning revolution. And after that, we have a new way of modeling the speech data. This is a deep neural network-based data modeling, which is the current phase. We call the TTS system in this phase neural TTS. So we can listen to the samples again and get a feel of the development of speech synthesis. So this is a signal processing simulation.
How are you? I love you.
This sample is from the hidden Markov model-based data modeling.
This is a sample speech generated with a hidden Markov model-based text-to-speech system. You can hear that the voice is rather robotic. The reasons are mainly twofold: the weak modeling power of the hidden Markov model and signal processing methods being used to generate the speech.
And finally, there is the DNN-based data modeling.
This is a sample speech generated with the latest neural text-to-speech system. You can hear that the voice quality is greatly improved. The major reason is that deep neural networks have much more modeling power than the previous method.
By comparing these samples, we can clearly feel the improvement in the development of a speech synthesis. Then finally, we reach the future directions of speech synthesis. All these are based on the deep neural network approach. Here's an overview of the future directions. By listening to the speech generated by the neural network approach, we can still hear that it's not as perfect as human speech. So a development for the future is to move closer to natural speech. In this case, we need to improve the prosody of the generated speech and also make it add some emotion to the generated speech. So that's one direction for future development. Another development is to increase synthesizing speed. Compared to the traditional approaches, HTS and the concatenative speech, concatenative TTS, the neural TTS is slow. So people are putting effort into increasing the synthesizing speed. And the major part is to develop a faster acoustic model and a vocoder. Another development is to decrease computing resource requirements. That's also another shortcoming of the neural TTS approach, because neural TTS requires a large amount of computing resource. A specific way of achieving this is to do network compression. I mean, a major reason of the higher computing resource requirement of the neural TTS is that the network is very huge. If we can reduce the size of the network, then it will require less computing power. The fourth direction is to reduce production costs. Again, neural TTS requires a large amount of speech data, and creating a large speech data set is very expensive because we need to hire higher quality speakers and use higher quality recording studios to build a speech data set. So those are very expensive. In order to make it less expensive, we needed to figure out ways of doing that, trying to use less speech data to build TTS systems. And final, but not last but not least, direction is to combine TTS technologies with other technologies, such as automatic speech recognition, machine translation, and even avatar. So let's look at some concrete examples of all these directions. A way of improving the quality of the generated speech is to integrate context features into the neural network. The diagram shows how we can integrate the context features into a Tachytron 2. Because the context features have a good important influence of the pronunciation of a particular phones. If we can integrate this kind of context features, then we will make the modeling easier, the task easier. In this way, we can improve the prosody of the generated speech from the neural TGS systems. And this is a general approach. Actually, this can be applied to many of the new acoustic models, including Tachytron 2 and Transformer. A way of improve the generation speed is to do parallel generation. In acoustic models we just talked about, and the Tachytron 2 and the Transformer, and they both had the disadvantage of autoregressiveness, which means we have to generate samples one by one, and the current samples have the current sample has dependency on previous samples. So in order to do parallel generation, you have to break this dependency. So that's the major task of this faster speech approach. In faster speech, it also has an encoder and a decoder, as the diagram shows. But between the encoder and the decoder, there's no attention. Instead, it has the variance adapter. A variance adapter, as the diagram left-hand side shows, it's just different models, including the energy model, the pitch model, and the duration model. So by using this variance adapter, then we don't have the dependency between this encoder and the decoder. I mean, there's no dependency between the current frame and the previous frames, because this model is separate. So essentially, the variance adapter in this faster speech architecture, it breaks the dependency between the different frames. And that's why it's much faster than the previous approaches. And in terms of network compression, we can do a neural network pruning. Pruning is a way to reduce the size of a neural network. Obviously, with a smaller neural network, we can do the inference much faster, because a smaller neural network, it requires less computation. And there are two basic ways of doing neural network pruning. We can either removing just a network connection. So that's the edges in a network graph. So we just move some of the edges to make the network smaller. That's one way of doing the pruning. Another way is to move a whole node directly, as the lower part of the diagram shows. We just move the node with all its edges in the graph. So this is a kind of a further pruning, a pruning in a large scale. In the first case, we just move some edges, but in the second approach, we moved a whole node with all the edges connected to it. In doing this kind of pruning, apparently we have to just remove the least significant connections or nodes. If we remove the connections or nodes with significant weight, then we've got a problem. The model will be changed, greatly changed. So common criteria used in a pruning is to remove nodes with close to 0 weights. So all those edges are weights in inference. So and the different edges have different weights. For many of the weights in a network, they are close to 0. So they played a very limited role in the inference. And that's why we can remove those without losing the quality significantly. A way of reducing the cost of building a TTS system is to do transfer learning. In a transfer learning, we first train a model with a bigger data set, and then we fine-tune the model with a small data set. So in this way, we transfer the knowledge learned in the first model, in the first model to the second model, to the improved model. And the big data set could be taken from a high resource language, and the smaller data set often are from the lower resource language. In this way, we reduce the cost because we only need a small amount of a data set for the from the low resource language. So this is a very effective way of building a TTS system of low resource languages. Here is an example which shows how we do a transfer learning, the effect of a transfer learning. In the first sample, it's just a normal English TTS system. We train the model with 13K sentence English data. And in the second example, we did a transfer learning. First, we trained the model with a 23K sentence Chinese dataset. And then we just use a 3K sentence English dataset to fine-tune it. So we are doing a transfer learning here. We can hear the sample and feel the effect of this transfer learning. So this is a normal TTS.
It had been for some time devoted principally to felons of the worst types.
And this is a result of doing transfer learning.
It had been for some time devoted principally to felons of the worst types.
We can hear that the quality of the generated speech are very close. But in the second case, we used a very limited amount of speech data for the target language. In this case, we use English, but in a real life scenario, we could use a lower resource language. This just shows how the transfer learning works for this particular purpose. Then finally, we reached another direction of the future development, which is combining the TTS technology with other technologies. A talking figure is a good example of this kind of combination. In this combination, speech generation and image generation are combined together. So since this is a combined effect, because there are correspondences between the speech and the image. When we training the model, we have to train a combined model, because the final results, there are interrelations. There are interrelations between the final two modes of the final product. But in other cases, we don't need to do to train a combined model. In a case such as a speech dialogue system, we can do a cascaded system. We can build a cascaded system. In this cascaded system, the different technologies are combined in a cascaded way. Specifically, in this speech dialogue system, we combine an automatic speech recognition system, a question answering system, and a TTS system together. But we combine it in a cascaded way. So we don't need to train a combined model. We just need to train the models separately and then integrate the system as a whole system. So finally, we go back to the basic task of speech synthesis. As we said, the basic task of speech synthesis is to let the machines talk like human beings. Now we'll ask the question, can machines talk like human beings now? Here's my opinion about this question. Based on the overview of the development of speech synthesis, we can see we have made a huge progress. From the very beginning, we are doing a physical simulation of a human vocal tract. And finally, we are using a deep neural network to do the speech data modeling. We can see we have made a huge progress. But even now, we are still far away from realizing the dream of speech synthesis, which is that machines talk like human beings. Because talking is very different than reading text aloud. So mostly, the current TTS system is still tries to read text aloud. And talking involves spontaneity. So that's the key feature of a human talking. And if we look at the current system, we're still far away from that final target. So we still need to make much effort in the future to move closer to the final target. Since this course is also about music signal processing, so in this slide, I briefly talk about the relation between singing and speech synthesis. Well, there's a big difference between singing synthesis and speech synthesis. Well, the major reason is that singing is much more complicated than talking. In talking, we're just pronouncing phone sequences. So just the phone sequences are involved in talking. But certainly we have some prosody, but the prosody in talking is not that complicated as in singing. In singing, besides phone sequences, we need also to use scores and also the alignment between scores and phone sequences. So anyway, the singing action is much more complicated than talking. So based on this, singing synthesis is also much more complicated than speech synthesis. Of course, we can transfer some speech synthesis technologies, some methods into the field of singing synthesis. But to do singing synthesis, we have to consider more factors. I think there are two aspects in this neural network approach. First, for the input, we cannot just use the phone sequences or the text. Besides the text and the phone sequences, we also need to input scores. So we need to figure out a way to also include the scores into the input. Another thing is the neural network also needs to be more complicated than speech synthesis. So these are the two major aspects in doing the neural network singing speech synthesis. So it is more complicated than just the speech synthesis. For those people who are eager to do some hands-on experience of hands-on work of building a concrete TTS system here's some guidelines. So today, I think the neural TTS almost replaced the traditional TTS, the HTS and the concatenative TTS. So these days, people often are just building a neural TTS. And there are many open source packages on the web for building a neural TTS system. Most popular one is ESP.NET. This is a very comprehensive package. It's built by the same group who built Kaldi. Kaldi is only for automatic speech recognition, whereas ESP.NET also has many other features, including TTS and also voice conversion and many others. So if you want to have use a very comprehensive package, you can try ESP.NET. But if you want to focus on TTS, this TensorFlow TTS is a better choice. TensorFlow TTS is also up-to-date, but it's dedicated to a TTS, so it can only build the TTS systems. It supports the most recent acoustic models and vocoders, including Tektron 2, fast speech 2, MailGAN, Hi-Fi GAN. Another important feature of TensorFlow TTS is that it also does model compression. So finally, you could build a TTS system that can be run only on CPU. So you don't need a GPU to run the final model. So that's the feature which the ESP.NET doesn't have. So if you want to focus on this building this TTS system, you can try TensorFlow TTS. And finally, if your machine is not that powerful, you don't have a very powerful GPU, you can run your final system on CPU only. And here are the major steps in building a neural TTS. First, you need to prepare the data set. And the neural TTS is still based on data modeling. So first, you need to have the data set. Fortunately, there are many open source data sets on the web. You can download there directly. A popular English data set is LJ speech. You can just Google LJ speech and to find that the download link. When you have the data set, you need to do pre-processing. The major task of pre-processing is to generate acoustic parameters. So with the package, you can just run some script directly. And then there is the training phase. Training includes acoustic model training and vocoder training. You have to train these two different kinds of models separately. After the model training, you can do inference or decoding. Basically, you just use the trained models to generate first acoustic parameters, and then based on that, you can generate a speech. And if you want to have an integrated system, you could integrate the two parts together to have a combined system. So these are the major steps of building the most recent neural TTS. Thank you for your attention. If you have questions, you could send an email to me to luyf@i2r.h-star.edu.sg. I will be glad to answer your questions. Again, thank you for your attention. I hope by this lecture, you have obtained a very comprehensive understanding of the key concepts and ideas of speech synthesis. And if you want to do further research, you could explore more materials on the web. Thank you. Goodbye.